Today's Rutgers experimental math seminar speaker is Eric Rowland from Hofstra University. A long time ago, a grad student at Rutgers University who will speak about Luca congruences modulo p square. If you have any questions, as usual, please unmute yourself, ask a question, and then mute yourself back. Thank you.
Yeah, feel free to ask questions throughout. Thanks very much for the invitation. This talk is going to be about Luca's theorem, which is about Pascal's triangle. So many of you have maybe seen this question before, but it's a very nice question. What does Pascal's triangle look like when you reduce all of the entries modulo 2? So if we color the odd entries blue and leave the even entries white, we get this picture. This is the first 8 rows. And then if we double the number of rows, then the picture is sort of a refinement of the picture that we saw before. So this is, yes, the Sierpinski, exactly. So this was when was Sierpinski? This is probably before Sierpinski. So Luca was working in the 1870s. And I don't know that he was looking at these pictures, but I think he must have been looking at these pictures because I don't know a way to figure out Luca's theorem otherwise. The first time you really see these pictures in the literature is in the 1970s and 80s, but that might be just because that's when it became feasible to print graphics like this. So here are the first.
Stephen Wolfram had a Christmas card a long time ago with this.
Oh, I don't know about, yeah. So one of the people who claims to have discovered this is Stephen Wolfram. He has a paper from the early 80s. So yeah, maybe I don't know about his Christmas card. So yeah, so many people have explored this pattern. Probably Luca in the 1870s. And one thing that Luca may have done is to look at subsequences in order to sort of understand the picture. We would call it a fractal. It has self-similar behavior, but this was half a century before Mandelbrot was born, so there was no notion of a fractal. But we could look at these 4 subsequences and notice that when you look at these subsequences, 3 of them look an awful lot like the original picture, and the exception is the subsequence 2n choose 2n plus 0 to choose 2m plus 1. That one is all even. So here is a formula, conjectural formula based on these pictures that if you have R and S that are base 2 digits, then you can write 2n plus R, choose 2m plus n, 2m plus s, using n choose m itself if R is not, well, if R is 0 and S is 1, then it's 0 mod 2, otherwise it's just n choose m. So what's special about R equals 0 and S equals 1? Why is it the odd one in terms of these pictures? Well, one way in which it's different is that 0 choose 1 is 0. Whereas the other 3 binomial coefficients, if you just look at the R over S, those binomial coefficients give you 1. And modulo 3, we see something very similar. So here we're using blue for 1 mod 3, green for 2 mod 3, and white for 0 mod 3. If we increase the number of rows, this is 27 rows and 81 rows. Again, we see some self-similar patterns here. And here we might look at 9 subsequences and notice that all of them are constant multiples of the original. So a lot of them are just 1 times the original. These are 0 times the original. And when we choose 2 and 1, it turns out that this is 2 times the original. So all the 1 mod 3s, when you multiply them by 2, become 2 mod 3s. And the 2 mod 3s, when you multiply them by 2, become 1 mod 3s. So this is one way that you could discover Luca's theorem. Going on to mod 5, this is the first 25 rows. I tried to generate a picture with 125 rows, but LaTeX complained that it ran out of memory. So that was too many hexagons for ticks to draw. But you would get the same thing. And this is what you would guess if you were Luca in the 1870s. If you take a prime P and you're interested in Pn plus R, choose Pn plus S, that it is congruent to n choose m, so the whole sequence scaled by some constant R choose S, depending on which R and which S you've chosen. All right, and if you iterate this, you can think of writing two numbers in base P. If the base P digits are N0 through NL and M0 through ML, then you can iterate this and break it up into pairwise, pairs of digits, of base P digits, form a binomial coefficient for each one, and multiply them all together, and that gives you the value of this big binomial coefficient modulo P. So what about non-primes? Here is Pascal's triangle modulo 6. This beige region over here looks like Pascal's triangle mod 2, and some other features remind you of Pascal's triangle modulo 3, which of course makes sense because the Chinese remainder theorem says that we can reconstruct a value mod 6 if we know its value mod 2 and mod 3. So really this picture is an overlapping of the mod 2 and mod 3 versions. And so we won't, unless we have access to the base 2 and base 3 digits, we won't be able to figure out what, some nice analogous formula for the n comma mth entry in this sequence. So it seems like there's no hope for a version of Lucas theorem modulo 6, but modulo 4, there's only one prime running around. And so there's a little bit more hope. So we might ask, does the original Lucas congruence hold if we just require it to, if we just bump up the exponent? So keep everything else the same, and we just want it to hold mod p squared instead of mod p. So here's one example with p equals 2. N is 1, m is 0, r is 0, s is 1. So we want this to just break up into the two pairs, 1, 0, and 0, 1. The binomial on the left-hand side is 2 choose 1, which is 2. And on the right-hand side, we have the 0 choose 1, so that will be 0. So unfortunately, this does not work. So in fact, this is a counterexample. These are congruent mod 2, but not congruent mod 4. But there are lots of other things you can say. So people have been interested in Lucas theorem and generalizations for a long time. There are lots of directions and variations. This is one that does work. So if you let the two digits R and S be 0, you do get a valid congruence that holds for all N and M. And this is of the Lucas type, because if R and S are 0, then 0 choose 0 is 1. So there's really a times 1 here. In fact, you can say something a little bit stronger than this. So Jakobstal in 1949 showed that if P is at least 5, then this congruence holds mod P cubed, not just mod P squared. And here is a generalization from 1990. It's almost a general Lucas type congruence, except the numbers have to be of a specific form. So if you think of the top and bottom as being written in base P, the least significant digits can be anything, R and S, but then you need 2 zeros after the least significant digits in the top and bottom because of this P cubed here. And in that case, you can break it up as n choose m times r choose s, and it works mod p cubed. There are lots of other papers about this.
You know the first name of Bailey? Is it David Bailey from Experimental Math fame?
I don't remember. I think it's not David Bailey.
Okay.
Yeah, but I can check. So there's actually a new question that you can ask about Lucas congruence, surprisingly, but it didn't occur to me until after I had found an analogous result for the Apery numbers. So the Apery numbers arose in Roger Apery's famous proof from 1978 that zeta of 3 is irrational. And in 82, Gessel showed that they also satisfy Lucas type congruence. So this is a one-dimensional sequence rather than a two-dimensional sequence. So in some sense, it's a little simpler. But Gessel showed that A of Pn plus D is congruent to An times A of D, mod P, where D is any base P digit. So here is the sequence of Apery numbers modulo 7. And here I've broken them into blocks of length 7 so you can kind of see the structure better. As soon as we know the first 7 terms, we can build each other block of 7. This block we get by multiplying this block by 5 modulo 7. This block we get by multiplying the original block by 3 modulo 7. And so again, it reflects the base P structure of n. So for example, if we want to know the Apery, the 2039th Apery number modulo 7, if we write it in base 7, then iterating this Gessel's Lukács congruence, this is a product A of 5, A of 6, A of 4, A of 2, which we can read off from these first 7 values. So the first 7 values determine the entire sequence. We just multiply these values together and we get to 3 mod 7. A few years ago, my co-author Reem Yasawi and I got into the business of studying sequences like this using automata. And then, yeah, it looks like a homomorphism, exactly. And then Doran and I actually wrote a paper about this as well. What this is another way to represent Gessel's congruence. So this comes exactly from Gessel's congruence. The way it works is if you're reading a number in base 7, you start at this node, and then every time you read a base 7 digit, you follow the arrow labeled with that digit. So here we're going to read right to left. So we start with, we read 2. If we start in this state and we read a 2, we go here. And then we read a 4, we go here. If we read a 6, then we loop back to this same node. And then when we read a 5, we end up here. And then the output is the value of the node where we finish. So the output would be 3 in this case, meaning that this number is congruent to 3 mod 7. And so since you know that if you compute the first 7 Apery numbers modulo 7, this is enough to build this picture, to build this automaton. The 0 and 6th Apery numbers are 1, so multiplying by 1 shouldn't change the value. So that's why we have a loop labeled 0 and 6 on every node. And the first and 5th Apery numbers are 5 mod 7. So if we read a 1 or a 5, then we multiply our value by 5. So really this is a cycle of powers of 5 in base 7. And if we read a 3, if we read a 2, 3, or 4, then those Apery numbers are 3 mod 7. And so we end up multiplying by 3, which happens to be the inverse of 5 mod 7. So we go the other direction around this cycle. And Gessel's congruence will let you build an automaton like this for any prime. So here it is mod 5. The first 5 Apery numbers modulo 5 are 1, 0, 3, 0, 1. And of course, if you are multiplying by 0, then whatever you multiply after that, you still get 0. So there's an absorbing state in this automaton. If you read a 1 or a 3 in your base 5 representation, then you enter this state in the middle here, and then you can't leave because you're just multiplying 0 by other numbers. In the same paper, Gessel also showed that you can strengthen the congruence in some ways. So modulo 9, this same congruence that held modulo 3 also holds modulo 9. So here's an automaton for the nth Apery number modulo 9. It's just saying that the congruence for the prime 3 also holds, and more strongly, it holds modulo 9. However, this is not true for other squares of primes. So modulo 25, for example, here's the first place where it breaks. So here P is 5. If we take A of 5 times 2 plus 1, this is A of 11, which is this big number. Modulo 25, you can see this is 0. But if we wanted to break it up in the Lukács way, we would want to get A of 2 times A of 1. That's 73 times 5, which is 365, which is not 0 mod 25. So this doesn't work in general, modulo P squared. But my co-author and I were computing automata like this. So here's an automaton for the Apery numbers modulo 25. This doesn't come from Gessel's congruence. This comes from another source. But here's what you get. It looks like a big mess until you start deleting some of the nodes. So if you delete nodes whose outputs correspond to multiples of 5, for example, 0, 5, 10, all these inner nodes in here, you do get a very nice cycle. And that's equivalent to restricting the digit set. So it turns out that whenever, we saw on the previous slide that if you read a 1 or a 3 in base 5, then the nth Apery number that you're computing is 0 mod 5. So ignore all those. If all of your base 5 digits are 0s, 2s, and 4s, then it does correspond to this very nice cycle. There is a Lukács congruence modulo 25. This is powers of 23 modulo 25, I guess, where reading a 0 or 4 doesn't change the value, and reading a 2 multiplies by 23. And this is where we stood for several years. This was 2015.
Eric, remind me the proof. Do you use the original definition of Apery numbers as a binomial coefficient sum and use some congruences for the binomial coefficients? Or
no, what we did was we used the fact that the Apery numbers are the diagonal of a certain rational function.
Ah, okay, yeah.
And did operations on the rational function in order to get this congruence. Yeah.
Thank you.
Sure. So at the time, I played around with the automata for the Apery numbers modulo 7 squared and 11 squared, but I wasn't able to see such a nice picture come out of it. And that's because I wasn't quite looking at it right. So more recently, maybe a year or two ago, I started, instead of starting with the whole automaton, I just started experimentally seeing which digits look like they support Apery number, Lukács congruences modulo 7 squared. And this you can do experimentally, right? So you're just looking for digits D such that A of, say, 7n plus D is congruent to A of n times A of D for modulo 7 squared for all n, right? So you can try the first 100 values of n fairly easily and see whether it works. And modulo 7 squared, this digit set seemed to work. And you get this big cycle, modulo 49. Here are the first, here are the Apery numbers corresponding to these digits and their values modulo 7 squared. So this seems to be the right digit set. So modulo 5 squared, the right digit set seemed to be 0, 2, 4. This seems to be the right digit set for 7 squared. 23 squared, we also seem to have a nice healthy set of digits that supports a Lukács congruence, modulo 23 squared. 0, 7, 11, 15, and 22 are the digits. And this is the picture. I've dropped labels and everything to make the picture a little less cluttered, but basically it's 2 cycles. It's powers of 415 and powers of 475. Sorry, 473 modulo 23 squared. And they cross over each other a bunch of times. So these are the values of these 5 Apery numbers modulo 23 squared. Here's just one more, modulo 59 squared. There also seems to be 5 digits that work. And this was all experimental initially. And here are the 5 values. You may have noticed something about all these 5 values, which is that they're symmetric, right? So these aren't just any 5 values. A0 and A58 are congruent. They're both 1 mod 59 squared. And A of 6 and A of 52 are also congruent to each other. They're both 460 mod 59 squared. And so this was a hint as to what the general characterization is of digits, base P digits that support Lukács congruences modulo P squared for the Apery numbers. And it turns out that if you look mod P and not mod P squared, the Apery numbers do satisfy a reflection symmetry. And we already saw that earlier in the examples. Maybe you noticed for when we looked at A of 7 and A of 5, A of n mod 7 and A of n mod 5. The first P terms were symmetric. This was proven by Amita Malik and Armin Straub. They showed that the Apery numbers satisfy this reflection symmetry mod P. And so it turns out that the base P digits that give you a Lukács congruence modulo P squared are precisely the ones where this reflection symmetry not only holds modulo P, but also holds modulo P squared. So if we define D sub A for Apery of P to be the digits, the base P digits that satisfy this symmetry modulo P squared, the theorem is that this congruence, this Lukács congruence, holds modulo p squared for all n if and only if D belongs to this set. So this set is not empty because p minus 1 over 2 is the halfway point, so that will always satisfy the reflection symmetry. You can also show that 0 and p minus 1, you can show that the p minus first Apery number is always congruent to 1 mod p squared, and a of 0 is 1. So a of 0 and p minus 1 will also always be in this set. So that explains why 0, 2, and 4 worked for the prime 5. The other digits that occurred for the prime 7 and 23 and so on, those are in some sense coincidences, but they're digits that satisfy this reflection symmetry modulo p squared, and therefore also let the Lucas congruence hold. All right, as of yesterday, this sequence is in the OAS. This is the size of D sub A of P, so the number of digits for the nth prime that this reflection symmetry holds modulo P squared. Here are the first several primes where this set is bigger than 4, or bigger than or equal to 4. So we know that for all the odd primes, we have at least 3 digits in this set. Here are the particularly big ones. So 107, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 digits in the set. This is an analytic number theory type question that I haven't thought about at all, but would be interesting to know is how, originally you could ask how big, what's the size of dA of P as P gets large. I think there's a little too much fluctuation, so maybe a better question is, what's sort of the average rate of growth if you take the partial sums, all primes less than or equal to x, what's the behavior of this? So I don't know, but if anybody's interested in thinking about that, I would encourage you to do so. Okay, so for Apery numbers, we have an answer to the question, when does Gessel's Lucas congruence hold more strongly mod p squared and not just mod p? So let's ask the same question. This was the question that it didn't occur to me to ask for binomial coefficients until it came up for Apery numbers. What is the set of pairs of base p digits, Rs, such that Lucas congruence for binomial coefficients holds modulo p squared? And again, we can do some experiments. For the prime 2, it seems that there's only one pair of digits, which is 0, 0. For the prime 3, it seems there are 3 pairs, also 3 pairs for the prime 5. We know that the pair 0, 0 is always going to be there because of this congruence. So this congruence always holds. So that is a Lucas congruence for R equals 0 and S equals 0. So there's at least one point in this set. Here is the set for p equals 7. There are 4 points. And at this point, I started plotting them graphically to sort of understand better where these were happening in the triangle. So R, the first coordinate is the row, and S, second coordinate is the column number, or basically it's the distance from this left edge of the triangle perpendicularly. So if these 4 pairs of digits always support a Lucas congruence modulo 7 squared, then if you happen to choose 2 numbers whose base 7 digits, when you take them in pairs, are always in this set, which isn't going to happen very often, but for those pairs of numbers where that does happen, you can compute the value of this binomial coefficient modulo 7 squared, just as you would compute it modulo 7 using the Lucas congruence, iterating the Lucas congruence. So this binomial coefficient should be congruent to 36 modulo 7 squared. Here are, let's see, what do I have next? P equals 11. Yeah, P equals 11 has a few more points. So there are 9 points in this set. And here's their distribution on the triangle. Here are some additional primes. And the thing that jumped out is that this set seems to possess the symmetries of the equilateral triangle. The reflection symmetry about the vertical axis maybe isn't so surprising because Pascal's triangle also has that symmetry. And so this does follow. After a little bit of work, you can show that if you have a point in the set D of P that supports a Lucas congruence, then its mirror image across the vertical axis is also going to be in D of P. But the rotation was much more surprising to me.
Very surprising.
Why should it be that if you have a point in a set, then when you rotate it 120 degrees about the center, that you also get a point in the set? Because the first P rows of Pascal's triangle mod P are not invariant under rotation, right? So here's mod 7, you rotate this 120 degrees, you don't get the same picture. So first of all, where does a point go when you rotate it 120 degrees? The only way I could figure this out was by decomposing the rotation into a composition of two reflections. Right, so the first reflection takes R comma S to R comma R minus S, same row, but reflected. And then if we reflect a second time and compose these two reflections, we'll get the rotation. This is the second reflection about this line. It takes this point to a point with the same second coordinate. So it takes R comma S to something comma S because it's the same offset from the left edge of the triangle. And this is just what it works out to be, P minus 1 minus R plus S. And so if you compose these two, you get the rotation. So that means that the orbit of this binomial coefficient, if you're at R comma S and you rotate 120 degrees, then you're at this binomial coefficient. If you rotate 120 degrees again, you're at this binomial coefficient. And then of course, you'll be back at R comma S. So there's something going on with these three binomial coefficients that if one of them satisfies a Lucas congruence, then they all do. Or it's an if and only if. So either they all do or none of them do, it seemed. So here's what's actually going on. Why there isn't a rotation in Pascal's triangle mod P, but there is a rotation up to sine. So this binomial coefficient on the right-hand side, let me flip back a slide, it's the second point in the orbit. So it's the point you arrive at after rotating by 120 degrees. And I did not know this before it came up in this project, is that these two binomial coefficients differ by a sign, modulo P. So here's an example for P equals 7. If we're at, let's see, what is this? It's 1 choose 0 is this 1 right here. And when we rotate 120 degrees, we end up at this 6. Well, 6 and 1 are off by a sign. It's exactly this sign. If we start at this 2 instead, and we rotate 120 degrees, we end up at this 5. 2 and 5 are off by a sign, mod 7. And the orbit of this 3 would hit 10 and then 4 and then back to 3. 3 and 10 are congruent mod 7 and they're congruent to -4 mod 7. So there is a rotation.
Was that not known before?
It was news to me. I mean, something that I've seen before, this bottom row, I know people know that alternates in sign ±1 mod 7, but I haven't found it anywhere. So I don't know.
It's pretty nice.
Yeah. So this is what's going on with the rotation. There's an underlying rotation modulo P, and when that rotation also agrees modulo P squared, that's the condition for when the Lucas congruence holds. So these two statements are equivalent. We have a point in this set that supports a Lucas congruence. So that is this congruence holds for all n and m modulo P squared, if and only if these three binomial coefficients that are rotations of each other about the center are congruent, not just modulo P, but also modulo P squared.
Are you gonna, Eric? Are you gonna look at Pascal's tetrahedron later on?
So yes,
And you'll get
I have
three-dimensional groups.
yeah, I have a student who's doing that right now. It's not quite as nice. At least it seems to. Yeah, I'll mention that at the end.
As long as I'm interrupting you, let me just mention that I think Bill Gosper looked at various other triangles from combinatorics, mod 2, and maybe mod 3, and so on. And it might be worth looking at some of those. They're all in the OEIS.
Okay.
You know, if you take Stirling's triangle mod 2, that kind of thing.
Right. Okay. Yeah. Thanks. Right. So for the Apery numbers, it was a reflection symmetry that when the reflection symmetry holds mod p squared, that's when you get Lucas type congruence mod p squared. And here it's a rotational symmetry that when the rotational symmetry holds modulo p squared, you also get Lucas congruence modulo p squared. And the way I was able to prove that these two are equivalent was by adding a third statement involving harmonic numbers. These two are equivalent to the statement that the rth harmonic number, the r minus s harmonic number, and the s harmonic number are all congruent mod p, not mod p squared. So this is the simplest test of the three of them. If you're actually going to find points where this holds, the third one is probably how you want to do it. Of course, the harmonic numbers are rational numbers, but if n is less than or equal to p minus 1, then there's no p's in the denominator, and so we can interpret the nth harmonic number by inverting the denominator modulo p. Here is the size of the set D of P for the nth prime. Again, I don't know anything about the sequence other than the terms are at least 3 after the first term. So it'd be nice to know more. Here's part of the mechanism that makes it work. So here's a general theorem for this expression. When this last piece is 1, that's exactly when you get a Lucas congruence. And you can arrange that by requiring these differences of harmonic numbers to be 0. So when HR minus H of R minus S is 0, and similarly this term right here is 0, then this entire term becomes 1, and you get your Lucas congruence modulo p squared. So this is part of the proof. There's some nice, since there's so much geometry here, it makes sense to, or it's natural to ask about like the center of the triangle. When P is 1 mod 3, then the triangle has a center. Otherwise, it doesn't necessarily have a center point that has integer coordinates. But when P is 1 mod 3, then the center does have integer coordinates. And so in that case, of course, when you rotate the center about the center, it doesn't go anywhere. So the symmetry, the congruence trivially holds modulo p squared. And so you do get a Lucas congruence modulo p squared. And this binomial coefficient actually has some history. It was studied by Jacobi, modulo p. And in 1989, Young just established its value modulo p squared. Its value mod p squared is negative a plus p over a, where a is the value in this equation when you write 4p as a squared plus 27b squared, and you choose the sign of a so that a is 1 mod 3. So that's the center of the triangle. Another geometric point of interest you might be wondering about is the midpoints of the triangle, midpoints of the edges of the triangle. So if you have one point in the set dp, then they all have to be in the set dp because of the rotational symmetry. And this turns out to be equivalent to the statement that P is a Wiefer prime. So,
that's pretty good.
Yeah, I was looking for a while. I didn't find any primes where the edge midpoints were in the set until I got to 1093. And that's a pretty good indication that you're dealing with Wiefer primes. So there's only 2 of these known. Yeah.
Very nice.
And when you have a Wiefer prime, it's known that this binomial coefficient is plus or minus 1 modulo p squared. So yeah, so lots of interesting geometry, lots of interesting number theory in this topic. I want to give some indication about why the harmonic numbers are arising, and that's because of this characterization. So this is, again, if you read this congruence modulo P, this is the congruence that holds always in the first P rows. And it holds modulo P squared precisely when these two harmonic numbers are congruent mod P. And the reason basically comes down to when you're expanding factorials, right? So the numerator of P minus 1 minus S, choose R minus S, is P minus 1 minus S factorial. You can write this as this product. And then if you expand, you want to sort of collect everything you can. So you end up with pulling out an S factorial in the denominator, and everything else is basically looks like a harmonic number. So this is where harmonic numbers arise. This is a common trick. This trick is not due to me. Everyone who's studied binomial coefficients, mod primes, and powers of primes does this to get information.
So Eric, can you extend it for mod P to the power K, where you have partial sum of the zeta Riemann zeta function at K?
Well, I didn't look at that, but I did look for the analog of the set D of P. So are there base P digits that support Lecoq congruences modulo P cubed and modulo P to the fourth? And the bad news is that experimentally, there seem to be very few. So modulo P cubed, the three corners of the triangle work, and you can show that. That's equivalent to Jakob Stahl's result that I mentioned earlier. But aside
no,
from
but for the more general statement where you had explicitly the harmonic numbers,
right,
that's valid for all RNS, right?
Right.
That's valid for all.
Yeah. So this theorem,
can you do something analogous for mod P cube, or in general, in replacing the harmonic numbers by the counterpart partial sums of zeta K?
Yeah, mod P cubed, you could do it. There's mod P to the fourth, maybe not, because there's an extra step where you have to get this n choose m somehow, and so here you're using a separate congruence to go from Pn choose Pm to n choose m. So and that I think only works mod P cubed. I don't think it works mod P to the fourth. So yeah, mod P cubed, you could definitely do it.
Okay.
And then I'll just finish with generalizations. So I have a student right now, Joshua Krisafi, who's looking at multinomial coefficients, because this is the obvious next thing to try to see if there are symmetries there. I'll show, these are 3D pictures. It's sort of hard to see the geometry of. So I'll spin some around in a second. But it turns out that through what he's doing, it looks like the 2-argument multinomial might be more natural than binomial. So of course, it's just a reparameterization of the same thing, but the orbit, this rotation, behaves a lot simpler in these coordinates rather than in these coordinates. So the orbit of r comma s contains these two other points, which just look a lot easier to work with, because here we have an r, here we have an s, and these other coordinates are the same, p minus 1 minus r minus s in both places. So let me show you the 3D versions. So this is for the prime 5. The origin is at the bottom left here. So there's some symmetry, but unfortunately it's not any extra symmetry in addition to the symmetry you would expect from multinomial coefficients having by definition. Here's the prime 11. So again, we get this rotational symmetry. There should be 6 equivalent points, because if you have a 3-argument multinomial ABC, there are 6 permutations of A, B, and C. So that is definitely what's going on, but there doesn't seem to be any extra geometric symmetry that we found on top of that. This is for the prime 19. You may have noticed this huge tetrahedron at the bottom. This is something that doesn't happen for binomial coefficients, but does happen for multinomial coefficients and higher order, 3-argument multinomial coefficients and 4-argument multinomial coefficients. And the reason is that once the sum of your 3 entries gets high enough, then you have to necessarily be divisible by, then your multinomial coefficient has to be divisible by p squared. So down here, when the arguments are high enough, it's very easy for the Lukather congruence to hold in a trivial way, in the sense that both sides are 0 mod p squared. So that's what he's doing right now. And I'll stop there. Thanks very much.
Thank you for a great talk. Please unmute yourself. Thanks for a great talk and beautiful pictures. We have plenty of time for official questions, and later on, you're welcome to stay for unofficial questions. But there's plenty of time to question. Any questions for Eric?
I
Okay,
have
so
a
I have a
question.
question.
Oh,
Go ahead.
I may have missed this, but the binomial coefficients extend to complex arguments, right?
Yes.
Are we able to ask related questions for these extended values of the binomial coefficients? And do we have answers?
I don't have any answers about that. The tricky part is that if you want something to be holding modulo p or modulo p squared, first you would have to figure out what you mean by, by a real number modulo p or modulo p squared. Yeah, so I don't know. I don't know if there's anything there.
Cool. Maybe something I'll be interested in.
Yeah.
Eric, so Apery numbers are famous for historical reasons, but in principle, you can take any binomial coefficient sum and ask the same questions. Have you done it, for example, sum of the cubes of the binomial coefficients or any other binomial coefficient sum?
So there's another sequence that's also called the Apery numbers that are associated with zeta of 2. I did try it for those, and I didn't see any nice symmetry going on. So yeah, I think there is definitely more work to be done. These are the only 2 cases that I know of right now. But yeah, I think that would be a great thing to do, is try it for a bunch of other sequences and see what we can find.
And the Apery numbers don't have anything interesting for p cube?
No, yeah, for p cubed, I think it's just a of 0 and a of p minus 1 that work.
So Eric, you just looked at the 2 things we call the Apery numbers. You didn't look at any of the other weird sort of sporadic binomial sums that come up in relation?
Maybe I looked at a few. I haven't done a super exhaustive search.
There's like 10 of them or something, right? 10 famous ones?
Right. Yeah, I don't think I've
Maybe
looked
less
at
than
all
10.
of them.
Okay.
Yeah.
Any more questions? Well, let's thank Eric again for a wonderful talk, and see you next week.
Thank you.
All right. Bye, everyone. We'll see you back here next week.
Okay. Bye-bye.